Today we'll be presenting EchoVision. Visually impaired individuals face significant challenges carrying out everyday tasks on their own. They often rely on external assistance just to read signs or navigate unfamiliar spaces, limiting their independence and autonomy. Globally, 2.2 billion people experience some form of visual impairment, of which 43 million are medically blind. Reduced autonomy can negatively impact mental health, career opportunities, and overall quality of life. How can we empower visually impaired individuals to live more independently and confidently without constant reliance on others? The current solutions out there are smartphone apps, handheld OCR devices, white cane guide dogs, and wearable devices, which all have their limitations. Our solution, EchoVision, captures the world through a built-in camera. It analyzes surroundings and provides real-time voice feedback on objects, hazards, text, and people. Then it enables hands-free integration through seamless voice commands. Here is our tech stack. Here's the hardware components that made our project possible. In our network diagram, we have an ESP32 where we have a camera and speakers connected to it. Then we have a Jetson, which we have button and mic connected to it. These two communicate over Bluetooth. For power, we use a battery that powers both the Jetson and the ESP32 in series. For the software diagram, we have a Jetson that runs two parallel processes. The camera capture process captures the camera from the camera server and stores it into a camera buffer, while the agent is reading the camera buffer. The ESP32 is running the camera server at all times. Our agent runs by creating a state and passing that state into our vision language model, which acts as a reasoning layer, interpreting that state and pass successful trajectories to assess the best course of action. Then the actions are taken using our toolkit. This is scalable because we can increase our toolkit, making our applicability larger, and then also the past successful trajectories can be used to make the model better. So as we collect more data on successful trajectories, our model gets better.
So here's going to be our demo. We have two of the capabilities of our glasses. The first capability is explaining our surroundings, and the second capability is getting directions.
Can you explain my surroundings?
Explanation of surroundings. The images depict an interior space with a large window showing a view of the outside. The window appears to be overlooking a cityscape with several buildings visible in the background. There are some furniture pieces, including a red chair or cushion, which suggests a modern office or living area. The walls are painted in a light color, and there is a device or panel on the wall, possibly a control panel or a decorative element. The overall ambience seems bright, likely due to natural light coming in from the window.
Can you take me to the nearest park?
Head south toward W. Woodruff Ave.
A key technical challenge is that throughout the hackathon, we realized that our original object detection model was too slow for real-time use, and we redesigned to instead use zero-shot inference with a VLM. This allowed us to make API calls to offload onto a faster and more powerful GPU rather than trying to run all of our object detection processing on board. For our next steps, we want to create faster model response time, a sleeker hardware design, more agentic capabilities, and multilingual support.